You can hold a conversation, but you would honestly rather not, and that quiet reluctance is the whole tell. Your breathing has climbed. It is elevated, steady, entirely under your control. Your legs register the work, and yet the work is something you could carry for the better part of an hour without stopping and without coming apart at the end of it. That specific band of effort, heavier than a walk and lighter than a run, is the only intensity where the tiny power plants packed inside your cells receive the one instruction that makes them multiply. Below that band, they simply hold their number. Above it, they get skipped over entirely. The band is thin, and what unfolds inside those cells at this one effort level, only here and nowhere on either side of it, quietly decides whether your body starts building more of the machinery that makes your energy, or keeps running on the same slowly shrinking set of plants it has been losing since you were somewhere around 30. So the question sitting underneath everything that follows is easy to ask and genuinely strange to answer. You already exercise in whatever form you have settled into. The plants are still declining anyway. What actually flips the switch that orders a cell to grow more of these power plants, and why might the exercise you already do be missing it entirely? Every cell that spends energy carries mitochondria, the microscopic plants that turn fuel into usable power. They take glucose and fatty acids and convert them into a molecule called ATP, which is simply the cell's spendable currency, and they do it through a chain of chemical handoffs called the electron transport chain. Picture a bucket line. Electrons stripped from your food are passed hand to hand down a row of proteins buried in the plant's inner wall, and each handoff releases a little energy that gets used to pump charge across that wall. The charge builds like water behind a dam. When it rushes back through, it spins a molecular turbine that stamps out the currency. More plants inside a cell means more bucket lines, more turbines, more capacity to make the thing every action you take has to spend. The very first bucket in that line has a name worth knowing, because it connects to a story you may already carry. The opening protein, complex 1, accepts its electrons from a shuttle molecule your body builds from the vitamin family and leans on for nearly every reaction of daily metabolism. That shuttle grows scarcer with age, which means each individual plant slowly loses a little of its own output over the years. Hold that thought, because it sets up something the whole rest of this hinges on. If each plant makes a little less currency as the shuttle thins, then the total power your body can produce depends heavily on how many you own to spread the shortage across. Fewer of them, each running slightly weaker, is a compounding kind of decline. These mitochondria can even be counted, indirectly, which is how any of this is known at all. Under an electron microscope, a slice of muscle shows the mitochondria directly, crowded or sparse, and a single enzyme buried inside them, citrate synthase, sits at the mouth of their central chemical loop in such reliable proportion to the mitochondrial population that measuring its activity in a pinch of muscle gives a clean read on how many plants are present. The number is a bench measurement, weighed from a pinch of muscle rather than estimated. That capacity is not fixed, and here is where age quietly enters the room. Age enters that count in a way worth seeing clearly. The plant population falls by roughly a tenth every decade of adult life in the snapshot studies that compare young muscle to old. Follow-up work that tracks the same active people across years shows a gentler slide, which hints that a good part of what looks like pure aging is really the accumulated cost of simply moving less as the decades stack. Muscle that keeps demanding power keeps its plants. Muscle that stops asking lets them fade. The afternoon crash, the shorter fuse for exertion, the sense that recovery drags longer than it once did. Each of those traces in part to fewer plants making less total currency across the day. One layer of the story about a fitness plateau that stops responding lives right here underneath all of it in a plant count that keeps drifting downward while you are not watching. Those plants are shrinking in number. A daily walk keeps the ones you still have alive and working. Whether that walk actually orders them to multiply is a separate question, and for most seasoned walkers the physics returns a quiet answer. Walking switches on a whole roster of genuinely good machinery inside you. It lifts a growth signal in the brain that helps you think clearly and hold your mood steady. It nudges an energy sensing switch inside the muscle, a kind of fuel gauge that trips when the cell's currency runs low and improves how well the cell reads and manages its own supply. It drags blood along the vessel walls with a gentle shearing force that the walls actually sense, and that sensing keeps them supple, reactive, quick to widen when blood needs to move. It swings open the little doorways in the muscle membrane that let sugar leave the blood and enter the fiber to be burned, which is a large part of why a walk after a meal settles your blood sugar so well. None of that is small, and none of it should be given up. For someone who has just laced up their shoes after years spent mostly on the couch, that walk genuinely does sit above the line where new plants get built, and the first months of feeling lighter and clearer contained a real, measurable gain in plant number. Then the body does what bodies do. It adapts. And the very same walk quietly slips below the line. Every order to build new plants runs through a master control protein with the unwieldy name PGC1-alpha, which you can think of as the construction foreman of the cell, the one who decides when the current machinery is no longer enough and it is time to break ground. That foreman only wakes up when the cell senses an energy shortfall deep enough to signal that the plants it already owns can no longer keep pace with what is being asked of them. For the seasoned walker whose body has already tuned itself to the walk, the effort drains the cell's currency at a speed the existing plants absorb without ever straining. The shortfall stays shallow, the foreman keeps sleeping, the mitochondria coast along, maintaining, building nothing new. There is a kind of cruelty in that. The thing that helped you most is the thing your body learned to handle, and in learning to handle it, stopped needing to grow for it. So if a familiar walk no longer reaches the foreman, the obvious human response is to push harder, climb the hill, chase the pace, feel the effort bite. Why on earth would harder effort fail to solve the very problem the walk could not? Push the effort high enough, into a sprint or a heavy interval or an all-out surge up a flight of stairs, and the demand for power outruns everything the mitochondria can supply. The plants are thorough but slow. The cell cannot afford to stand around waiting for them when the muscle is screaming for currency this second, so it falls back on a faster emergency route called glycolysis, which produces the cell's currency in a tearing hurry, but wastes most of the fuel doing it. The trade is steep. Glycolysis wrings only a couple of units of power out of each sugar molecule, where the plants, given time and oxygen, would have calmly extracted more than a dozen times that much from the very same molecule. You are paying roughly 15 times the fuel for speed you can only sustain for seconds or minutes. It is the metabolic equivalent of burning the furniture to heat the house quickly. It works, right up until it cannot. Here is where it gets visible. The moment the switch flips can be caught without any needle at all, through the air you breathe. Physiologists track a number called the respiratory exchange ratio, which is simply the balance between the carbon dioxide you breathe out and the oxygen you draw in. Burning fat pulls a lot of oxygen and returns relatively little carbon dioxide. Burning sugar in a hurry returns proportionally more. As you climb past that oxidative ceiling and glycolysis takes the wheel, that ratio drifts upward in a way a mask and a gas analyzer can read in real time. The crossover from fat to sugar as your main fuel is a measurable point on a curve readable in the air you breathe, and you can feel its aftermath directly. Lactate piles up. That familiar deep burn in the working muscle is a flood of hydrogen ions thrown off by fast glycolysis, overwhelming the muscle's ability to mop them up and hold its chemistry steady. The plants were leapfrogged out of sheer necessity. The message they receive says only that the emergency route already handled the crisis on its own, so the mitochondria have no reason to grow. They stand down. None of this makes hard effort worthless. Very hard effort does force its own adaptations, and they matter a great deal. The heart stroke grows stronger and moves more blood with each beat. The buffering systems that neutralize that acid burn improve, and the whole body gets better at tolerating and clearing lactate so you can hold harder efforts longer. Both a hard interval session and the middle band we are circling do reach the construction foreman to some degree, since both create a real energy shortfall. The difference is duration. A hard interval is over in a minute, and the shortfall vanishes with it, while the middle band holds that same build signal switched on steadily for the better part of an hour. That long, unbroken hold is what drives the largest gains in raw plant density, and the endurance capacity that high effort builds improves through channels of its own, as Hollow-Z characterized across decades of work on how exercise remakes the interior of muscle. Walking sits under the line. Hard effort vaults clean over the mitochondria and leaves them idle. Somewhere in the gap between those two extremes there has to be a place where the plants are driven right to their ceiling and still left holding the job. Where exactly is it? That place has a name people toss around without ever feeling its edges. It sits at roughly 60 to 70% of your maximum heart rate. The cleaner definition, the one written in physiology rather than in gym slang, is the highest effort at which fat is still your main fuel and lactate holds at or below a low, steady level of about 2 units per liter of blood. A threshold Millen and Brooks mapped through careful metabolic testing of what fuel the body actually burns at each rung of effort. Here is the whole trick of it, and it is worth slowing down for. At this one effort, the mitochondria are running flat out. They're prying fatty acids apart in a process called beta oxidation, snipping the long fat chains 2 carbons at a time and feeding each piece into that central chemical loop, and at the same time feeding sugar through the very same loop at rates that sit close to the very top of what they can physically manage. That loop is the plant's true engine room, where the carbon from your fuel gets fully unwound and its electrons handed off to the bucket line to make the currency. The demand for power is high enough that every last plant you own is fully committed to the task, and it is low enough that the emergency route has not yet been called in to help. Fat is doing the heavy lifting. The plants are the whole show. Hold on to that balance because it is the entire point. Now picture a factory running at the exact edge of its full capacity. Run that factory at half its output and no manager anywhere sees the faintest reason to break ground on a second building, because the one they have is loafing. Slam it instead with an order 10 times larger than it could ever fill, and the whole job simply gets shipped off to a faster outside contractor while the factory itself sits untouched, bypassed, quiet. But hold that factory right at the lip of full capacity, every line moving, every worker committed, fresh orders still arriving faster than they can quite be filled, and one single signal finally makes complete sense to send up the chain. Build another factory, so the foreman reads that exact condition and nothing else will do. Capacity fully spent, demand parked hard against the ceiling. More of them the only remaining way to buy more room. And so the foreman fires. The instruction travels from the muscle down into the cell's nucleus, where the genes live. The plant's own private strand of DNA, a small loop of genetic code each mitochondrion carries separately from the rest of the cell, begins copying itself. New mitochondria take shape as existing ones stretch long and pinch cleanly into 2, a splitting the biologists call fission. The population climbs, one patient division at a time, and it keeps climbing for as long as the effort keeps returning to the window week after week. That whole wake-up call, the path from a sensed shortfall to the master foreman switching on, was traced by Hood in foundational work on exactly how muscle assembles new mitochondria, and the full molecular relay from a single bout of exercise down to the gene it activates was later established by Egan and Zirith in a sweeping account of the signals that a hard effort sets loose inside the cell. Sit with how specific that is for a moment. This window is narrow for one clean reason. Both conditions have to be true in the very same instant. The demand must be high enough to genuinely strain the mitochondria and gentle enough to leave them as the main supplier of power. Drop below the band and the strain never arrives, so the foreman is never called. Climb above it and the emergency route grabs the wheel, and the plants stop being the bottleneck that would otherwise be begging for more of themselves. Only in the thin seam between those two failures does the signal exist at all. The window is real then, and the physics behind it is clean. So how on earth do you find this precise effort inside your own body, standing in a park with no laboratory anywhere near you? Your own voice turns out to be the first instrument, and you see, a surprisingly good one. The reason it works is quietly elegant. Speaking cleanly requires steady, controlled airflow, and the moment your breathing rate climbs to feed a harder effort, holding a smooth, full sentence starts to compete with the breath itself. So the exact point where a whole sentence becomes just slightly inconvenient to finish maps closely onto the exact point where glycolysis is about to start contributing. Your lungs are reading your metabolism for you. At the right effort, you can still push out a full sentence, but you would genuinely rather save the breath and not bother. You can keep the effort going for half an hour to a full hour. Your breathing runs deep and rhythmic, never ragged, never gasping. The walker stranded on a flat, familiar daily loop is sitting just below this place. A hill added to the route. A faster pace held on purpose. A shift onto a bicycle or down into a swimming pool at that same, slightly reluctant effort. Any one of these carries them up off the flat and into the window at last. Your pulse is the second instrument, and a rougher one than most people are told. It lands at roughly 60 to 70% of your maximum, and the old rule of subtracting your age from 220 gives only a crude opening guess at where that maximum sits. A guess that frays further with every year you add. Your breath and your own honest sense of the effort read the window far more truthfully than any formula printed on the side of a treadmill. Chat away with complete ease, and you are underneath the band. Manage one whole sentence, but need to steal a breath before the next one, and you are brushing right against its upper edge, which is roughly where Jacobs and Lundby quantified the way oxygen use climbs across these efforts when they measured trained and untrained legs side by side. Blood lactate is the third instrument and the most exact of the three. A reading that holds at or below steady level confirms you are genuinely inside the window, and the word steady is the physics of it, not a throwaway. Your body is always producing a trickle of lactate and always clearing it, and at low efforts the clearing keeps easy pace with the making, so the level in your blood sits flat and calm. The upper lip of the window is the exact effort where production and clearance still balance, where the muscle is making lactate briskly, but the rest of the body is soaking it up just as fast. Push a single notch past that balance and production starts to win the race. Lactate accumulates faster than it can be swept away, the level in your blood begins to rise rather than hold, and that rise is the physical signature of the emergency route switching on and the build signal thinning with every step past the line. And the lactate itself does not simply pool as waste. Your heart and your slower muscle fibers pull it back out of the blood and burn it as fuel of their own, which is exactly why the level holds steady inside the window and only climbs once production finally outruns every place that can soak it up. The gold standard sits in a small pinprick of blood. Your voice and your breath are the field version of the same reading, and you carry them with you everywhere you go. Now comes the practice of it. You feel the effort, you hold it, you keep the plants working hard without ever tipping them over the edge into bypass. Hold that for a session, then another, then weeks of them. What actually changes inside you as they accumulate? Nothing dramatic announces itself on the first day. The opening 2 to 3 weeks mostly sharpen the mitochondria you already own, tuning up the enzymes packed inside each one so it runs a little cleaner and squeezes a little more currency from the same fuel. This is fast because it asks for no construction at all. The cell is simply making more copies of tools it already knows how to build and stuffing them into plants that already exist. That early lift you feel is real, and it is not yet new machinery. Building the machinery itself takes longer, and it happens in a different way. Genuinely new mitochondria only become measurable somewhere around the 4th to 6th week, because assembling one is slow work. That private loop of genetic code inside each plant has to be copied in full, fresh proteins have to be manufactured and threaded into new inner walls, and only then can an existing plant stretch long and pinch cleanly in two to hand its contents to a daughter. Copying code and splitting a living structure simply cannot be rushed the way copying a single enzyme can. A full shift in density, a visibly denser crowd of them packed into the muscle when a slice of it is finally viewed under a microscope, asks for 8 to 12 weeks of steady, repeated visits to the window. 2 weeks of effort and a shrug polishes what you already had and leaves you standing at very nearly the same plant count you started with, the tools a little sharper, the number unchanged. Learning that the new plants do not even begin to appear until deep into the 2nd month is the single thing that stopped me abandoning the effort at the 3-week mark, which is precisely where I had quietly given up every previous time I tried. Then, slowly, the body starts to feel different. The downstream effects gather slowly and then settle into feeling completely ordinary, which is, of course, its own kind of wonder. Each cell makes more currency across the day. Your tolerance for real exertion rises because a task that once demanded nearly everything your old plant count could produce now sits well within a larger reserve. Your capacity to burn fat as fuel climbs as a larger crowd of mitochondria processes more fatty acids every single minute. The afternoon crash softens, and here is the quiet beauty of the arithmetic. That thinning shuttle molecule from the very start of this, the one that leaves each individual plant a little weaker with age, matters far less when you simply own more plants. A larger population pulls more total power even from a shrinking per-plant supply. Building more of them is how the body partly answers a shortage it cannot otherwise reverse. The sheer volume of oxygen your body can use at full stretch goes up. The fine web of tiny vessels feeding the muscle grows denser to keep the fuel and the oxygen arriving where they are spent, and that denser web shortens the distance any single molecule of oxygen has to travel from the blood to the plant that burns it. More mitochondria, fed by more vessels, each a shorter hop from its supply. The whole delivery chain thickens together. And this is where the old plateau finally gives. A fitness ceiling that stopped moving no matter how faithfully you walked was sitting, all along, on top of an energy foundation that had quietly stopped growing underneath it. The walk kept the floor swept. It could not raise the ceiling because the ceiling was set by how much total currency the muscle could produce, and that number is set by the plant count. Widen the foundation and the ceiling lifts with it. The thing that felt like a hard wall was really the top of a shrinking base. There is one boundary here worth naming plainly, the one the physics draws hardest, a clean edge around what this effort can and cannot do. This middle band effort expands the energy machinery, and it leaves a completely separate signal untouched. Growing the muscle itself demands mechanical tension, a genuinely heavy load. The fiber is physically forced to resist, and tension is a different language spoken to a different foreman altogether, the one that governs the building of new muscle protein rather than new power plants. That second foreman only listens to force. It reads the strain of a heavy load through the architecture of the fiber and answers by ordering the muscle to lay down more of itself. The endurance band, for all that it does inside the plants, never puts that kind of strain on the fiber, so it never reaches that second foreman, no matter how long or how faithfully you hold the effort. These two signals do not overlap, and that is the part worth carrying home. You cannot substitute one for the other, because they answer to different demands and build different things. A complete rebuild of the aging body therefore asks for both instruments at once, the endurance band to multiply the mitochondria that make your energy and real resistance work, a load heavy enough to strain the fiber, to trigger the muscle to grow. One expands the engine, the other enlarges the frame that carries it. Skip the resistance and you can end up with a well-fueled body that is quietly still losing the muscle that spends the fuel. And the seasoned walker who was stuck breaks the plateau at last because the energy foundation lying underneath it finally widened, though the walk alone, faithful as it was never going to be the thing that widened it. Here is where it left me. I kept the walks and moved the plant-building work up into the reluctant band, letting the walking settle back into being exactly what it always was, a foundation to stand on rather than an engine to grow. You can hold a conversation, but you would rather not. Your breathing is elevated but controlled. Your legs feel the effort, but it is sustainable. That narrow band is the only intensity where your mitochondria are working at near maximum oxidative capacity while remaining the primary energy source. Below it they are coasting, above it they are bypassed. At this intensity, the master foreman reads the signal that mitochondrial capacity is fully used and demand is at the ceiling. The transcription begins. New mitochondria form. The population grows. The energy-producing machinery the body has been losing since 30 begins multiplying inside the cells that need it. The walk was the foundation. This is the intensity that expands the foundation. The mitochondria were always capable of multiplying. They were waiting for the signal that said the current number was no longer enough.